Hello, welcome. Yeah, so I'm back with another video, and this time a bonus example on the squeeze theorem, aka the sandwich theorem, and in France called the police theorem. Yeah, okay, cool. And what we have to do is figure out what this limit is using the squeeze theorem. Now, okay, we know that what the squeeze theorem says is that, like, if we've got like f of x, in this case this function, if it's bounded by two other functions, let's say g of x on the right and h of x, my bad, I need the space there, okay, you'll see, and then h of x on the left, so f is squeezed in by h of x and g of x, then if we know that the limit as x goes to some number a of h of x, this here is some value L, and we also know that the limit is x goes to a of g of x, this here is some number L, then we can automatically say that the limit is x goes to a of f of x is also equal to L, because, well, as we tend to a, this limit and that limit for the two functions that are bounding or squeezing f is the value L, then that must also. So you know the visual, like the visual is like this could be like g of x, it's on top, f of x can be some crazy function that we cannot find the limit of at some x equals a over here, so x equals a is right here, right? And then h of x is below f of x, so it could do any crazy thing at once, h of x, but it's below it. Then clearly we're saying that they have to like have the same limit as x goes to a. Okay. So we get this. This is not so hard. Neither the statement nor the visual is hard. So why are these squeeze theorem questions hard? Well, because you have to come up with the functions h of x and g of x that bound your function f of x. That's what's hard about the squeeze theorem, right? Like there's that famous sine theta over theta, and we figured out cosine and the constant 1 are the ones that bound sine theta over theta, but we were very inventive and had to do a lot of interesting geometry to get there. Watch that video if you'd like. The limit is x goes to 0 of sine theta over theta. No, sorry, the limit is theta goes to 0 of sine theta over theta, or the limit is x goes to 0 of sine x over x. And that's one, by the way, but yeah, check out that video. So here, what do we do? Well, anytime you have sine or cosine, you should already know from our experience that -1 is a lower bound for sine of theta, and +1 is an upper bound for it. All right, and so this is always a good place to go to anytime you need to bound sine or cosine, right? Okay, and it doesn't matter what theta is, right? Theta here is pi over x. It'll still be true that -1 is less or equal to sine of pi over x is less or equal to 1, right? Okay, so let me write this distant. -1 is less or equal to sine of pi over x is in turn less or equal to 1, right? Okay, now if I take this inequality, now you might see why I wrote them distant, and multiply on all three parts, this part, this middle part, and the right part, by square root of x cubed plus x squared. So I multiply by square root of x cubed plus x squared here, and then here also square root of x cubed plus x squared. And then here also I have 1 times, and so I don't even need to write the 1, square root of x cubed plus x squared. I see that I have found my correct h of x, which is this. It's negative square root of x cubed plus x squared, and then g of x, which is that, and so I know f is squeezed in, right? And crucial to all of this was this instrument, right? Okay, cool. And now we go, all right, what's the limit as x goes to 0 of h of x? Well, that's just 0, fine. And what's the limit as x goes to 0 of g of x? That's also equal to 0. So this 0 and this 0 represent the L. So then we say limit is x goes to 0 of our middle guy, our middle function, f of x is also equal to 0. And so this limit here, so replacing question mark with a 0 is all we've got. Yeah? Okay, cool. I hope you enjoyed this. Keep watching. Take care.